2006, question 27 on P-n junctions. So light of frequency 6.7 times 10 to the 14 Hertz. You may have noticed I kind of typed that out on your question paper because there was a wee misprint there. Is produced at a junction of a light emitting diode. So this is an LED. Describe how the movement of charges in a forward bias LED produces light. Your description should include the terms electrons, holes, photons and junction. So in an LED, what you're looking at is electrons and holes combine, and they combine at the junction, this division between the P-type and the N-type material. So electrons and holes combine at the junction and release energy in the form of a photon. That's the simplest way to say that. So in all of these sorts of situations, it's all about electrons and holes combining. They release energy in that process, quite often as heat, but in the case of the LED, when they combine, they release light energy, and that's all to do with the position of the depletion layer in relation to the top of the semiconductor. Part 2. Calculate the wavelength of the light emitted from the LED. Well, you know what frequency it is, you're given the frequency, and you know that all photons will travel at the speed of light. So 3 times 10 to the power 8. The frequency is 6.7 times 10 to the 14. You solve for lambda. Lambda is 4.48 times 10 to the negative 7. Or 448 nanometers. So somewhere in the visible light range. B. Use information from the data sheet below to deduce the colour of this light. So you're looking at something that's around about 450-ish nanometers. 434 is sort of blue-violet, and 410 is violet, so it's somewhere within the blue region. Blue-green 486, so it's between blue-green and between blue-violet, so it's probably just going to be blue. Blue would be fine as an answer there. Part 3, table below gives the work function for 3 metals, so it's relating it to the whole sort of idea of the photoelectric effect. Light from the LED is now incident on the metals in turn. Show by calculation which of these metals, if any, release photoelectrons with this light. Well, all photons, whether it's ones involved in the photoelectric effect or ones involved in semiconductors, they're subject to the same equation, and that's E equals HF. The energy of the photon is what we're trying to figure out. Planck's constant is 6.63 times 10 to the negative 34. You'll find that in the data sheet. The frequency is up here, 6.7 times 10 to the 14. Answer you'll get is 4.44 times 10 to the negative 19 joules. That's only half of that question though. You've got to figure out whether it's going to eject electrons or not. Remember, the work function of a metal is the minimum amount of energy required to eject an electron from its surface. What they're really looking for you to say here is whether electrons are ejected or not. So that number, 4.44 times 10 to the negative 19, is bigger than this number, it's bigger than this number, but it's not bigger than that number. So you're looking at photoelectrons being ejected from cesium and strontium. Second part there, deliberately I gave you this question because it's got a wee bit about diffraction ratings and stuff, and it's always good to kind of keep up to speed on that sort of stuff. So light from the LED has a wavelength, gives you the wavelength. Spacing between the lines on the grating is given, that causes the light to split and interfere in certain ways. Constructive interference is going to give you the bright areas here, destructive interference is going to give you the dark areas in between. So the equation for a diffraction rating for a maxima, because you're looking at a second order maximum here, is n lambda equals d sine theta the path difference equals d sine theta. The path difference for a maxima is n lambda, it's whole numbers of wavelength. So that's 2 if it's the second order maxima. The wavelength is 6.35 times 10 to the negative 7. The spacing between the gratings is given, you don't have to do 1 over the number or anything here because it's actually just given straight off. It's 5 times 10 to the negative 6. And you're solving for sine theta. Sine theta will be 0.254. Theta is 14.7 degrees. So it's tying together a question about p-n junctions with a bit of the photoelectric effect and a little bit of diffraction gratings as well.